All right, welcome. This is going to be our last new information lecture. Everything after here will be a review. So we're going to talk about, I obviously didn't say this because it should have said at the top here, constellations and cosmology. So let's get right into it. So looking at constellations, it's fun to look at constellations. I enjoy it. And so, one of the things that is most accessible to people in science is observing the stars and wondering what's going on. And for all time, people looked up the sky and fantasized about, there's a god, or and by God I mean like a Greek god or something, and it is always filled the imagination. So I want us to try to at least have a little understanding of observing constellations. So this picture here shows people looking at constellations. And of course, it has it has connect the dot things to tell you what is what. And so we have, Hercules here, and we have Corona Borealis, the Cygnus, the swan right here, Vega there, Sagitta, Delphinus, always one of my favorites, Pegasus, all of these constellations. Well, what are they? How do we find them? That's what I want to look at first. So when you're sky observing, the first thing you need to do is to learn a constellation that you'll always be able to find. And for most of us, that's either going to be the Big Dipper or the Little Dipper. So the Big Dipper and the Little Dipper, neither of them are constellations, by the way. They're what we call asterisms. An asterism is a star picture that's not a constellation. So here's the Little Dipper. And if you look at this picture, I'm going to erase that diagram. If you look at the picture, the stars are bigger or smaller to try to indicate which one's brighter. So Polaris is very bright. And Polaris sits just off of the celestial, I missed a syllable, the celestial North Pole. So that means that it's always going to be in the same position as viewed from Earth. As if you go out every night and stand in the same place and look in the sky, and you point in the direction of Polaris, it'll always be the same direction you're pointing. It's not going to move around. Everything else is going around that as the Earth rotates. But Polaris is going to be stationary. So that's a really good thing to be able to find. It's the bright star at the end of the Little Dipper. But what most of us can find, because it's generally brighter stars, is the Big Dipper, this thing right here. And so what I recommend, if you're going out viewing the sky, the Big Dipper is what we call circumpolar. The Big Dipper, by the way, is part of Ursa Major. The big bear that looks something like that. And we always laugh because bears apparently don't have tails, and both Ursa Major and Ursa Minor, which the Little Dipper is effectively the same as Ursa Minor, have tails. But if you can find that Big Dipper, these last two stars in the cup will guide you to finding the North Star. And you always, if you're here 40 degrees north latitude or somewhere nearby in the United States, the Big Dipper should always be visible in the sky. Any time of night, it'll be visible. So you find the Big Dipper, you follow those last two stars, and it points you to the North Star. Now you have your bearings. Now you can start finding other things based on their relative positions. So the next thing this points out is if you follow the arc of the tail of the Ursa Major, it brings you to Arcturus, which is part of the constellation Bootes. Bootes, I know it's supposed to be some warrior, but to me, I view it as the ice cream cone. That's Bootes to me. And what are these? I don't know, maybe a stand to hold the ice cream cone in place. So if you can find the Big Dipper, you should be able to find the North Star. Very useful for determining locations because it's always going to be pointing north wherever you are on Earth. And the Little Dipper and Bootes. Now, identifying a constellation in the sky is not as easy as it looked in this picture. So here we have, in the upper picture is a constellation, the lower picture is a constellation. The lower one is one I'm familiar with. It's easier for me to identify because of familiarity. First thing I want to point out is you see how this here looks lighter, looks kind of like a cloud? That's because that's part of the Milky Way. As we talked about in the last class period, the Milky Way is our galaxy, and the disk of the Milky Way is right here. And so this constellation is in the middle of the disk of the Milky Way. This is, if I do a connect the dot picture, you see there was a star there, star there, star there, star there, star there, star there. Those stars together make what we call, I'll call it the Northern Cross. It's an asterism, so it's not very definitively defined. You can't call it the Southern Cross because that's a different thing. So that forms a cross, but that's an asterism. That's not the constellation. The constellation here is a connect the dot picture that goes like this. And then you draw in the rest of the picture and you have a swan. That's my best version of the swan. So looking at just the sky, you don't really see that swan, do you? But you have to have in your head what the picture is. Now, this one above, you've got some bright stars here, and so you can start saying, well, I could see putting together something like this. You know, what is this, some kind of backward question mark? Well, if we go further with this, we would go like this, and then we say, ooh, that's some crazy shape that I can't really name. And we do, of course, have a name for it. This is Leo. Leo the lion. This one here was Cygnus. Boy, Cygnus. I think that's how it's spelled. And so these pictures over to the right show us what the actual constellation is. It shows the connect the dot picture in green here, what I did there in red, except for my last line apparently was way off. But then it has something else. The actual outline you see here is technically the constellation. Constellations are areas in the sky. They're not just a connect the dot picture. So that area, any star that's in that area is part of the constellation Leo. If we come down here to Cygnus the Swan, we have the swan outline, as you can see here. But then this whole region, this roughly rectangular shaped region, all of that is Cygnus. So these stars out here are also part of Cygnus the Swan. Now, every star belongs to one and only one constellation. And so the entire sky is mapped out with 88 constellations. And they cover, like I said, the entire sky. Somewhere around 48 of them are ancient. That is, people long ago said, oh, that looks like a giraffe. So that's going to be Camelopardus. But then they didn't fill in the sky, and so they made about 40 that are modern, that are things like Triangulum. Oh, look, there's 3 bright stars in this region. You can always make a triangle with 3 bright stars. So we're going to call this constellation Triangulum or Microscopium. I don't know how you're going to see a microscope in the sky, but there you go. So constellations, any part of the sky that you point to is part of a constellation. The trick is knowing which one. So, you recognize these constellations? Here, I don't see this picture of a lion at all, but artists will make these grand pictures because you know what? We're using our imagination when we look at these, and our imaginations fill in a lot of details. And so these are pictograms that go with the constellations. There is no official picture for any constellation. I've seen variations. Funniest thing I ever saw was an app on my iPhone that drew the swan like this, with its head where its butt is. That star there, its name literally means the butt, and they had the head there. I laughed. They eventually fixed the app because, well, somebody figured out that's backward. Now, when we identify locations in the sky, we identify them with 2 things. The declination, which is equivalent to latitude. Latitude tells you how far north or south you are of the equator. So Lincoln is at 40 degrees north latitude. Declination is the angle in the sky north or south of the celestial equator. Remember from our last lecture, the celestial equator is simply taking the Earth's equator and expanding out to that, quote, celestial sphere, the model that we know is wrong, but makes it easy for identifying locations. So if you are standing in Lincoln at 40 degrees north latitude, then your zenith, the point that is directly overhead, is going to be at 40 degrees north declination. So declination and latitude are very similar. Right ascension is roughly equivalent, but not the same. Oh, that wasn't supposed to happen. Right ascension is roughly equivalent to longitude, but yet completely different. So longitude measures how far you are east or west from the prime meridian. Well, right ascension, because the Earth rotates and it takes us 23 hours, 57 minutes, and some odd seconds to do, I think it's 57, maybe it's 56, to do one rotation as measured by the stars, 24 hours to do noon to noon on average, but you have to do a little bit more than one rotation, go noon to noon, because the Earth is orbiting around the sun. So what astronomers have done is they've set 0 right ascension to go through, I think it's the vernal equinox. This 0 right ascension we call the equinoctial couleur. And if you get up and your zenith is at 0 hours right ascension and you wait an hour, then the whole sky will have rotated and your zenith is now going to be at 1 hour right ascension. If you wait another hour, the sky will have rotated and you'll be at 2 hours right ascension. So the right ascension is measured in time because it makes it easy for, well, how are things going to move with time? It shows you the progression of how things are going to move over you with time. So if we're at Lincoln, this is the path that's going to pass overhead right here. And if you come out and this is overhead when you start, an hour later, this is going to be overhead. Now, you look at this sky map, and this is even harder to pick out than when you look at the sky. You know, I'm looking for constellations. Now, it helps me out a little. It shows me like, oh, this is Andromeda. But how do I identify Andromeda from this picture? Well, it really is kind of tough because I can't see where the great square of Pegasus is. And the head of Andromeda starts at the corner of the great square of Pegasus. And we can't see Aldebaran there where it starts. We can see over here we have M31. That is the Andromeda Galaxy. That is the only galaxy that's visible to the naked eye in the northern hemisphere. And like I said, we don't have enough reference here to actually pick out the constellation Andromeda. I'm pretty sure this is one foot, this is the other foot. And if you were to come up, you'd have like, here's one leg, and here's, well, something like that. There's the other leg. And it comes up to her head up here somewhere, but you can't see all of it. Here's a constellation that you probably recognize. This is, of course, Orion. We have Orion's armpit. That's Betelgeuse. Actually, it probably says in the picture to the left. Oh, no, it doesn't. That's Betelgeuse. Here's his front foot. That's Rigel. Notice the colors are so different between Betelgeuse and Rigel. Betelgeuse has a reddish color, and you can see that it's reddish if you go out and look at it, whereas Rigel has a bluish color. Those tell us things about the stars. Betelgeuse we call a red giant, G-I-A-N-T. Wow, I don't know how a D came out of my pen. It's a red giant. It is a star that is pretty massive, but in its dying stages. Rigel would be a blue supergiant. It's a young, very massive star. And then there's other stars here that I don't remember their names. But there is Orion. Orion's belt is a very well-known asterism, collection of stars. And this here is Orion's dagger or sword. Now I'm going to erase that box because if you look here, you see that it looks a little different there in the center. It doesn't look the same. Well, what's going on is this region right here is a region where we have lots of star formation. It's a big cloud of gas, and we're seeing light from that big cloud of gas there. I believe that when Ellen White talks about seeing the second coming, I believe she specifies that it's coming from that region. So that's a constellation that a lot of people know. It's something that I like to be able to point out. And you can look at picture drawn here for Orion and the other constellations nearby. There's Canis Major down below, and it has the star Sirius, called the dog star because it's the brightest star in Canis Major, which is the big dog. And it's the brightest star we generally have in the sky. Monoceros. Mono is one, Ceros is horn. That's a unicorn. We have Gemini up here, the twins, Castor and Pollux. We have the Taurus, the bull that he's fighting. There we have the Hyades, which is the V shape of the horns of the bull. Just going to move on. I don't know why that appears again, but it does. Now we're switching into cosmology. That's the end of our observing the sky section. Cosmology is about understanding our place in the universe. In our understanding of our place in the universe, the story really starts with Edwin Hubble in the 1920s. Before the 1920s, people pretty much believed that the Milky Way galaxy made up the entire universe and that things were pretty much static. But in the 1920s, Edwin Hubble discovered that the Andromeda, what they thought was a nebula, which is a cloud, was actually another galaxy separate from our own, that it was outside of our galaxy. And furthermore, when he observed stars, he estimated their positions by observing their luminosity. That's how much light they give off, and their brightness, which is how much light we see. So that's light we see. And this is light they give off. Why are those different? Well, imagine you're standing, or you put the headlight of a car right next to your eyeball and it's on. It is incredibly bright, right? The light you see is incredibly bright. If you walk away, you get to be a mile away from that car and you look at the headlight, it doesn't appear very bright at all. But it's got the same luminosity, it's giving off the same amount of light. But because of the distance, you see it far fainter. In fact, the brightness is proportional to the luminosity divided by the distance squared. So if you double the distance between you and a car's headlight, it's going to look 1/2 squared, or 1/4 as bright. And so using this, what Hubble observed was that stars that are farther away are moving away from us faster. Almost every star is moving away from us, but the farther away they are, the faster they're moving away. And so Hubble said, well, everything's moving away. Let me make a graph. And so he made a graph. I'm going to come back to this. He made a graph and he plotted the distance away and how fast they're moving away from us. And he found pretty much a straight line. And so he said, I have a relationship, a straight line relationship, that says the speed at which something's moving away is equal to the distance it is from us times some slope that is named the Hubble constant after Edwin Hubble. So, according to Hubble, from his observations, which have been studied more since he died and have been refined to show that he was definitely right, everything's moving away from us. The farther away, the faster they're moving away. Well, if we turn time around, if we go back into the past, everything would be coming closer together until you would come to a time when everything was at one location. And this brings us to something that is, of course, very consternation building in creationists like me. So let's ask yourself a few questions before we move on. If the distance between your eye and a lamp, like the headlight of a car, is halved, that is, here's the headlight of the car, and you start by observing out here at some distance d, and then you move to half of that distance, and you observe what happens to the brightness. When you get closer, is it going to get dimmer or brighter? I think we could all agree from experience it's going to get brighter. So I'll cross out the two dimmers. And then how much does it get brighter? Well, you have cut the distance in half. And remember, our relationship was brightness is equal to luminosity divided by the distance squared. So if distance is cut in half, 1 divided by 1/2 is 2. And so we're going to have that squared 4. It's going to be 4 times brighter if you get closer, cutting the distance in half. What I did before was I said if you started here and moved back, then your distance would be 2 squared is 4, and it'd be 1/4 as bright. Now, redshift is another important thing. You might have heard of the Doppler shift. Doppler shift. That's the effect that when something is coming toward you and making a sound, you hear the pitch up a little bit higher. So you hear a higher pitch as something's coming toward you, but if it moves away, you hear a lower pitch. And so you hear as something passes you. That's the Doppler effect. Well, this effect also occurs for light with the same relationship that when when an object is approaching, light shifts to higher frequencies. And when it's moving away, it shifts to lower frequencies. Well, in the visible spectrum, we have red is the low frequency edge, and blue is the high frequency edge. So if something is moving toward you, it's going to shift to high frequency, and we call that a blue shift. If it's moving away from you, it's going to shift to low frequency, and we call that a red shift. So Hubble observed that everything's moving away. So which kind of shift do they have if everything's moving away? Moving away shifts to lower frequency, so the red shift. So he observes all of the stars actually have a red shift. There's only a very small number of things that have a blue shift. So just to make sure we understand this shift, how will the spectrum of a star moving toward us change? So moving toward us, think about the car. The car's coming toward you, and when it's coming toward you, you hear, ee, and then if it passes, you hear, ee. So coming toward you is a higher pitch or higher frequency. Going away from you, a lower pitch or a lower frequency. So if it's coming toward us, it's going to be a higher frequency. Now, the question didn't ask about frequency, it asked about wavelength. Well, wavelength, remember lambda was the symbol for wavelength, is equal to the speed of light divided by the frequency. We use C as the symbol for the speed of light. So if it's moving toward you, F is going up. But if you're dividing by a bigger number, then lambda is going down. And so the wavelength is getting shorter, which is also moving toward the blue. So it will be shorter, compressed, making it a blue shift. All right. According to Hubble's law, the universe is expanding. And when we talk about the universe expanding, things get confused. And this picture is not an accurate picture, but it's a way to think about space. Now, space is three-dimensional. That is, we have left, right, forward, backward, and up, down. 3 dimensions of space. The surface of a balloon is 2-dimensional. Basically, you can go left, right, forward, backward, but you can't go in and out because you're on the surface of that balloon. So keep in mind, this is not a perfect analogy. But the idea that scientists have about what's going on with the universe right now is that the universe is expanding, which means you have objects that are on the surface of the balloon. So you can take a balloon and you can put little dots with a felt tip pin on the balloon, and you can measure the separation of the dots, and they might be 1 inch apart. But if you blow that up, the dots get farther apart. So you might measure later, it's now 3 inches between each dot. Well, did the dots move? With regard to the rubber, they didn't. They stayed where the ink stayed on the same pieces of rubber. So the dots didn't move, but the separation between them got bigger. And that's what scientists believe is happening with the universe, that the universe is expanding, that space is expanding. So the solar system stays put, and Alpha Centauri stays put. But the space between the sun and Alpha Centauri is slowly getting larger, even though neither of them is moving, because of the expansion of the universe. And the red shifts that we see are not the result of actual moving of the stars with respect to space, but it's the result of the space stretching. I know it's a confusing idea. So, what does Hubble's law really have to do with? Is the universe contracting? Is it expanding? Is it steady? We haven't mentioned cosmic microwave background radiation yet, so we can rule that out. We believe that the universe is expanding. Before Hubble, we thought it was steady state. But now we believe the universe is expanding, and that's what we have from Hubble's law. So a natural outcome, if everything is expanding, then if we go backward in time, it was contracting. And so there's a time when everything would have been one location. And so this is the beginning of what we call the Big Bang Theory. Now, when it was first proposed, it didn't have this name Big Bang. And there was a scientist, Fred Hoyle, who was doing research on nucleosynthesis, on creating different types of atoms. And Hoyle was a staunch atheist. He believed that there was no God. And when this whole idea came that the universe right now is expanding, so if you extrapolate back, you had to have a time where everything's at one location, and that's when the universe began. Hoyle said, what could make the universe begin like that? Nothing. There's nothing in nature that can make it. Scientists still don't have a good explanation. They have some real hand-waving stories, but no explanation for how the Big Bang could have started. And so Hubble absolutely rejected the idea of a Big Bang because he was an atheist. And he said that is absolutely, it would require you to believe in a God to believe in the Big Bang. So he rejected it. In fact, the term Big Bang came from him being interviewed, and he was talking about this expansion. He said, so, I mean, what made it all start? Was it just some Big Bang? And scientists said, hey, yep, that pretty much covers it. And that's how it got the name the Big Bang Theory. It was something that he was using kind of derisively as like, this doesn't make any sense. And they said, well, that's exactly what we're saying. So let's talk about this Big Bang Theory. The Big Bang Theory says that 13.8 billion years ago, there was nothing. There was no universe. It wasn't an empty universe. It was no universe. And then suddenly, out of nowhere, an enormous energy is deposited. And that causes the space, and the space grows. It grows rapidly. And as it grows, it cools. And as it cools, you start forming things like electrons and protons. And as it continues to cool, you form helium nuclei. And that's pretty much the end of it. You don't form anything beyond helium. And you get out to around 300,000 years after this Big Bang, this magical explosion, and it gets cool enough that electrons can suddenly combine with hydrogen atoms to form, or with protons to form neutral hydrogen atoms. You can see we're using physics ideas, we're using chemistry ideas here. But when you suddenly can form these neutral hydrogen atoms, something miraculous happens. Before this time, which is called the recombination, even though there's no re to it, it's the combination. There never was a proton and electron bound together before the recombination. And that's what's combining in the recombination. All of a sudden, light, which was basically travels from A to B and gets absorbed, then gets emitted, goes from B to C, gets absorbed. Light was really not able to get out. Just like light inside of the sun can't get out. It's bouncing all around in there. And it has to get out to what we call the photosphere before it can escape. Well, it was the same type of thing. Light was bouncing around within the universe, but it was constantly being absorbed and emitted. But then when you reach this time about 300,000 years after the Big Bang, suddenly the light's not getting absorbed, so it just keeps going and keeps going and keeps going. So in this picture, you see it says 380,000 years for its time. I've seen 500,000 years. I use 300,000 years. That's when the universe becomes transparent, and then light continues to travel. And so in theory, then, we're sitting here today. We should have light coming to us today from that period, according to this slide, 380,000 years after the Big Bang. And so this was proposed as people were studying the physics of what happens when something expands. When it expands, it's going to cool. And so they call this the cosmic, and I'm going to skip a word, background radiation. Now, I skipped a word because there's more to discuss about this. It was a super hot universe at that point. Obviously, it was super hot, just cooled down enough for electrons to stick to hydrogen, to protons to make hydrogen atoms. So the radiation at this time would have been probably ultraviolet. But what happened in the intervening times? Well, we had the expansion of the universe. And with the expansion of the universe, you have the redshift. And so everything should have redshifted from that original ultraviolet. So you redshift from ultraviolet, you get down to blue. You keep getting going, you get down to red. You keep going from red, you get to microwave. And so, well, yeah. So you have, it's not ultraviolet anymore, it's now microwave. So you have this cosmic microwave background radiation that was predicted back in the 1940s, but they did not have any equipment that was capable of observing this cosmic microwave background radiation. So it kind of went on the back shelf. I have evidence for the Big Bang, and we're going to go through a bunch of pieces of evidence. So let me not forget anything here. We currently see expansion of the universe as observed by looking at, stars that are farther and closer from us. That cosmic microwave background radiation has been observed, but it was predicted before it was discovered and measured. So you can't say, they found it, and then they said, let's make up a story to explain it. They predicted it should occur, and then it was found. And I must have my slides out of order because I have some pictures of Penzias and talking about that. Then there's measurements of element abundances. That's, of course, what Fred Hoyle was working on. And what Hoyle and other scientists discovered is that you have first hydrogen has one proton. Then you can have deuterium, one proton and one neutron. You can have tritium, one proton. Okay, it won't let me do that apparently. And two neutrons, or you can have, I give up, or you can have helium with two protons and one neutron to give it 3. Then you can go to helium-4. So you have 1, 2, 3, and then this one here was 3 as well. 1, 2, 3, 4. You can get those by adding one proton at a time. There is a mechanism to create neutrons from protons, but there is no element that is stable that has 5. No element that's stable with atomic mass of 5. Which means that if you're adding things by colliding protons with things, because the universe would have been almost exclusively protons, you really aren't going to make anything that's bigger than atomic mass 4. Now, there is a very rare opportunity that you might have 2 protons hit something with 4 at the same time and go to 6. So you can go on and make something with 6 and 7, but there's also no element with 8. So proportionally, there should be very low amounts of any element that has more than 4 nucleons in it, and virtually nothing with over 8. And so as scientists look at the abundances of elements in gas out there in the universe, they find that it matches this sequence, saying, okay, the nucleosynthesis matches what we worked out in the lab. Now, I have to point out another thing about Fred Hoyle. Remember Fred Hoyle? He rejected the Big Bang Theory because it required a God, and he was a staunch atheist. But as he was studying this nucleosynthesis, he got to studying carbon. That's supposed to be a C. And in studying carbon, he came to the conclusion that the atom for carbon simply couldn't exist unless the nuclear energy level for the carbon was exactly this value. Any small little variation, and it simply couldn't exist. And then doing experiments trying to measure it, he found that that's indeed what it was. It had exactly the only value it could have to exist. And Fred Hoyle, the staunch atheist, said, that's not possible. It's not possible that a randomly developed universe could have exactly this energy level in the nucleus. And so he decided that there must be a God ultimately. He rejected the Big Bang Theory because he was an atheist, but then he decided there had to be a God because carbon exists. And now, I don't want you to get the wrong impression. He did not become a Christian or anything like that, but he believed that there had to be a God, that there had to be some kind of ultimate power, some designer that designed the universe. And now I'm going to inject my interpretation here as a Seventh-day Adventist Christian on what I think about the Big Bang Theory. The Big Bang Theory is supported by a number of scientific measurements. We have 3 of them listed here. And you'll notice 2 of them are it's matching the prediction, right? They predicted these things before they even measured them. That's the way the scientific method works. Remember, on the final exam, you're going to have to go through the scientific method. You observe something interesting, you make a hypothesis that explains why it occurred based on existing scientific knowledge and ideas, and then you make predictions and test those predictions. And so predictions were made that there would be a cosmic microwave background radiation and that there would be specific elemental abundances. And then as technology developed, it wasn't even available at the time these were predicted. They found that the actual measurements matched the predictions. So I believe that while science has no explanation for what caused the Big Bang, I do. I believe in a God. I believe that God created all of the laws of nature that we've been studying in this class this year. And then God put energy in. He created the universe by putting energy in. And then the universe grew into what it is today, following the laws of nature that God had made. So ultimately, that means I believe the universe is 13.8 billion years old. I believe that God set these laws and he put in the energy and it followed his laws. And then at a different time, not at the beginning of the Big Bang, God came to earth. And as the Bible says, the earth was void and without form, and the Spirit moved over the deeps, the oceans. And then God terraformed the earth and created life on the earth as described in Genesis chapters 1 and 2. So I do not put the age of life on earth to be anything associated with what we get from when we were talking about geology. We have the Phanerozoic is 541 million years ago to now. I don't believe those are correct ages for life on earth, but I do believe that 13.8 billion years is correct age for God creating the universe and getting us to now. Okay. It is important to me that I give you some of my own personal belief as a Seventh-day Adventist Christian. So scientific evidence does give us an age for the Big Bang. What is it? Well, some of these are numbers you should have seen before. Let's just go through them. 6,000 years ago, that's a creationist, young Earth creationist, I should say, age for Earth, life on Earth. That is, if you follow Ussher's chronology, you go through the Bible and you read in Genesis and it talks about Adam lived so long and he beget Seth, and then he lived so many more years. And Seth lived so long and then he begat Enos, and he lived so years. And you follow those genealogies, and then you get to the flood and you go through, okay, so the time from the flood to this was this many years. That's Ussher's chronology. Bishop Ussher is the person who developed this. Ellen White was a firm believer that this was an accurate interpretation of the Bible. And that gives you about 6,000 years from when we start the age of Adam, which may be when he was expelled from the Garden of Eden, or maybe when he was created. But it gives you an age of roughly 6,000 years. So that is a valid date that you will hear lots of people putting for the age of life on earth. And some people interpret the Bible to say that the beginning of creation week, that's day 1, was also the day when the universe was created. And so they say that's also the age of the universe. Now, that's not a scientific answer. That's a theological answer. There's nothing negative or wrong about being a theological answer, but it's not the one that we study in the science class. There's nothing that means the science one is the right one. The science one is the one that we can explain using our human minds and our understanding of nature and not invoking God. Now, 100,000 years is often used as an over-under for creationists. 5 billion years, that is roughly the age of the earth and sun. We have the oldest rocks found on Earth are about 4.3 billion years old. And we have, looking at the sun right now, what its luminosity is, how much light it gives off, that is, and how much mass it has. We can do calculations to say that it's about halfway through its lifetime. Its lifetime should be about 10 billion years. So the sun's about 5 billion years old. So that's the sun and Earth age. And the 13.8 billion years is the age of the universe as determined by science. So how do we get that? Well, back to the microwave background radiation. The microwave background radiation, like I said, it was predicted in the 1940s, but they didn't have anything that could measure microwaves. And so they kind of let it die out. I mean, it's a theory that we all loved. Well, I wasn't alive then, but that you had no evidence for. Well, in 1964, Arno Penzias and Robert Wilson were working at Bell Labs, trying to develop what we now use as our cell phone communications. And they were systematically identifying sources of noise in the microwave spectrum and how they could get rid of them. And they found one source of noise that was in all directions and they couldn't get rid of it. They tried all kinds of things. This, you can see the picture here, that's their telescope. That's their microwave telescope. And birds would nest in there. Pigeons would nest in there. And so they're like, maybe it's the pigeon poop. So those two guys got in there and they scrubbed and scrubbed to clean it up. No difference. They thought, well, maybe it's just too warm. And so they used what's called a cold thumb to cool it down. Didn't make any difference. And they were just like so baffled. And at the same time, a researcher named Dickey, I think it was Dickey, was planning on writing a grant to do microwave study, to look for this cosmic microwave background radiation. And then somebody read about the problems that Penzias and Wilson had that they couldn't explain. They're like, they found the microwave background radiation. They weren't looking for it. They were trying to get rid of noise, and they found this noise. And so it's been studied extensively. And it is that microwave background radiation that gives us the 13.8 billion years age for the Earth. That is the gold standard that scientists use for the age of the Earth, is studying that cosmic microwave background radiation. It also tells us about the geometry of the universe. The geometry of the universe we believe to be flat, which means that Euclidean geometry works. That is, the area for a circle equals pi r squared for Euclidean or flat geometry. But you could have a geometry that's like being on a ball. We call that closed. But if you draw a circle on the ball, so you have the radius measured here, because of the bending, the area of that circle is actually less than pi r squared. The final geometry is an open geometry, which is kind of I can't draw. I really can't draw this for saving my life. It's a kind of saddle shape. And if you draw a circle on that, the circle is going to end up with the area of the circle is greater than pi r squared. And so looking at the cosmic microwave background radiation, they're actually able to determine that the area follows this pi r squared and that we have a flat universe. What's important about a flat universe? It implies what the end state is. If we have a closed universe, the end state is crunch, what is called the big crunch, the opposite of the Big Bang. Big Bang expands out, then it stops expanding and comes back in, and you have it crunch. That's what would happen if we had a closed geometry. The open geometry gives us the big rip. That is, things are getting farther away, and they continue to get farther away as time goes until everything is just isolated. And so being flat, we asymptotically approach equilibrium. It allows for a universe to last a long time. Both of these, we wouldn't still exist. We'd either already be isolated or already being in the big crunch. Okay, so this is just reviewing things that we've already talked about. The evidence is for the Big Bang. And I want to end the lecture with 75% of all matter in the universe is hydrogen and 25% is helium. And this is of all matter we measure. But that's not everything that exists. In fact, okay, I got to skip over a lot of pictures here to get, okay, that was it. Dark matter. Dark matter is matter that we can't find. We can study the effects of gravity and determine how much mass is present, and then we can look for objects and determine how much mass we see. And we see approximately 4% of all matter. About 75% of matter is, quote, dark matter. That is, it's causing gravitational attraction, but we can't find it. About 21% is dark energy. It's causing things to be pushed apart and we can't find why. And only 4% is stuff that we can measure. And to me, that really is a good place for me to stop and pause and think. What do we as humans really know? Everything we know about the entire universe is based on only, to the best of our knowledge, 4% of what's out there. The other 96% we're completely, absolutely ignorant about. And it seems ridiculous then to be so full of ourselves to say, oh, we've got this all figured out based on that 4%. And so it takes a lot of faith to believe in something like evolution. It takes a lot of faith to believe in something like creation. But in my mind, it takes a whole lot more faith to believe in evolution and the human understanding of things. I mean, we know that we're missing so much than it takes to believe in the Bible, which I see a lot of things fulfilled. So that's where we're going to end our lectures. The lectures following this will all be reviewed, preparing for the test. I hope you have a great day.